Welcome to This Explainer. Today, we're going to unpack the fascinating, totally invisible grid system that wraps around our entire planet and makes, well, pretty much all modern navigation possible. Seriously, if you've ever wondered how a delivery driver magically finds your exact front door, or how those massive cargo ships cross trackless, empty oceans without getting completely lost, you are in exactly the right place.
Think about it for a second. Long before we had GPS and internet-connected phones in our pockets, human curiosity was already driving us to explore. From crossing mountains to crossing deserts, we were always on the move. But as we ventured further out, we hit the ultimate navigator's dilemma. How do you avoid getting completely lost on a giant spinning sphere? Like, how do we pinpoint our exact location when the only things around us are endless sand or seemingly infinite waves? Okay, so here's our roadmap for this explainer. We'll start with our planet's big picture, then move to modeling the Earth, check out parallels of latitude, meridians of longitude, and finally, how to locate specific places on Earth. All right, let's jump right into Section 1, our planet's big picture. Since the very beginning of human history, we've always been traveling, trying to discover the absolute beauty of planet Earth. But obviously, our ancestors didn't have a digital map to just efficiently guide them to their destinations. Nope, they had to rely on looking really closely at their environment. Eventually, they realized they needed to invent tools, things like maps and globes, literally just to figure out exactly where they were standing in relation to the rest of the world. Now, if you zoom way out and look at pictures of the Earth taken by satellites, the very first thing you'll notice are these incredibly large landmasses entirely surrounded by water. These, of course, are our 7 continents. They range from the absolute biggest, Asia, which by the way is home to India, the 7th largest country in the world, all the way down to our smallest continent, Australia. Throw in Africa, North America, South America, Antarctica, and Europe, and you've got all the massive terrestrial puzzle pieces that make up our world. And surrounding all those landmasses are our 5 major oceans, not to mention smaller bodies of water like seas, gulfs, rivers, and bays. When we're talking about the heavy hitters, the major oceans, we've got the Pacific, the Atlantic, the Indian, the Arctic, and the Southern Ocean. The Pacific is an absolute giant. It's the largest and the deepest of them all, while the Arctic Ocean sits at the total opposite end of the spectrum, as the smallest. But hey, here's a really interesting little fact for you. The Southern Ocean, the one that surrounds Antarctica, it's actually our newest ocean. No joke, it only officially received its name back in the year 2000. It's just a great reminder that our understanding and really our mapping of the world is a constantly evolving science. So moving on to Section 2, let's talk about modeling the Earth, specifically globes. So we needed a way to study all of this, right? That's why we created the globe. It's basically a 3-dimensional miniature model of the Earth. It's designed to be an almost perfect copy that represents our planet in a really simple, highly accurate way. It even rotates, exactly like the real Earth spins on an imaginary axis between its 2 endpoints, the North Pole and the South Pole. But let's be honest, globes definitely have their limitations. You can only see one half of the Earth at a time, they aren't great for showing specific places or landforms in high detail, and honestly, they're pretty tough to carry around in your pocket. To give you an idea of just how seriously we take these models, get a load of this. Back in 1997, the Guinness Book of World Records gave the title of World's Largest Revolving and Rotating Globe to a model named Eartha. It was built to represent the Earth exactly as it's seen from space. It literally took 2 full years to build, and it weighs a staggering 2,500 kilograms. No way that's fitting in a backpack. All right, Section 3. Let's dive into parallels of latitude. To solve the problem of pinpointing locations on that spinning model, we had to draw some lines. These imaginary lines running from east to west are called parallels, or lines of latitude. Try picturing them as horizontal rings wrapping all the way around the Earth. Aside from the poles themselves, these parallels are complete circles, and because they're parallel, they are perfectly, equally spaced, and they never, ever intersect. Plus, since the Earth is a sphere, the lengths of these circles actually get shorter and shorter as they move further away from the bulging middle of the planet. So let's look at the key markers here. The whole system starts with the equator, right at 0 degrees latitude. It is absolutely the most important one. It's often called the Great Circle because it perfectly slices the Earth into the northern and southern hemispheres. From there, we map outwards to 90 degrees north at the North Pole and 90 degrees south at the South Pole. And as we move towards the poles, we pass some crucial boundaries that divide the Earth into climatic zones.
We've got the Tropic of Cancer at 23.5 degrees north, the Tropic of Capricorn at 23.5 degrees south, the Arctic Circle up at 66.5 degrees north, and the Antarctic Circle down at 66.5 degrees south.
Now for Section 4, Meridians of Longitude.
Okay, so horizontal lines alone are great, but they aren't quite enough to pinpoint a specific spot. For that, we need vertical lines to complete the puzzle. Enter meridians, or lines of longitude, which run vertically from north to south, and they behave very differently from latitudes. First off, all meridians are the exact same length. Second, they are definitely not parallel. The distance between them is at its widest right at the equator, but then they taper in and actually intersect with each other right at the poles. And when they do cross those horizontal latitude lines, they intersect them at absolutely perfect right angles. Basically, we use these vertical lines to measure our east-west distances.
Now, the starting point for longitude is 0 degrees, which we call the prime meridian. This is the line that divides the Earth into the eastern and western hemispheres. Back in 1884, an international conference officially decided that the prime meridian would pass through Greenwich in London, and the longitude line directly opposite to it, exactly on the back of the globe, is 180 degrees, otherwise known as the International Date Line. But history is packed with really fascinating localized systems. For example, early Indian geographers actually used the city of Ujjain as their own 0-degree prime meridian to start all their calculations. Pretty cool, right?
So if you're going to lock in one crucial point of comparison between these two sets of lines, let it be this. Latitudes run east to west, they are completely parallel, they vary in length, and they center on the equator to measure north-south positions. Longitudes, on the flip side, run north to south. They all meet at the poles, they are completely equal in length, and they center around the prime meridian to measure east-west positions. Got it?
Which brings us right to our final section, Section 5, Locating Places on Earth. Let's put all the pieces together. When you take those horizontal parallels and layer them with the vertical meridians, they form a single, unified grid all over the globe. This grid is the ultimate answer to that ancient navigator's dilemma. Because these lines intersect, if you have both a latitude and a longitude coordinate, that single exact point of intersection gives you the precise location of absolutely anything on planet Earth. Let's actually put this into practice. Let's say you want to find the exact location of the city of Chennai. You don't need to manually scan a massive paper map anymore. You just follow 3 simple steps. Step 1, find the 13 degrees north parallel of latitude. That tells you how far north of the equator you are. Step 2, find the 80 degrees east meridian of longitude, which tells you how far east of the prime meridian you are. And step 3, just drop a pin exactly where those 2 specific lines cross. And boom, you are in Chennai. It's precise, it's elegant, and it's perfectly mathematical. As we wrap up this explainer, let's do a really quick rewind and lock in those fundamental truths. Our planet is beautifully vast, right? So we study it using a 3D model called a globe. To navigate it, we use parallels of latitude. Those are the horizontal circles centered around the equator that divide north and south. Then we cross those with meridians of longitude, the vertical lines converging at the poles, centered on the prime meridian, dividing east and west. Woven together, they form this incredible master grid that maps our entire existence. Which leaves us with one massive, kind of mind-boggling thought. Think about it. From the mapping software in your car to international aviation, right down to the global supply chains routing your food delivery tonight, absolutely everything relies on this exact mathematical grid. So ask yourself, how quickly would our highly connected, ultra-modern world collapse into total chaos without these entirely invisible, completely imaginary lines? Thanks so much for learning with me today, and keep exploring.